All right, so today we'll start by talking about threading, our threading system, and then if we have time, I'll talk a bit about our test systems too. So threading and timing. The goal of threading is, of course, we have these new computers which have a lot of cores, many more than we used to have, and we want to use them as well as possible. So we want to maximize the throughput through our system, which in a game, the throughput is typically how fast we can process, update, and render a frame, or the FPS if you want to use that. But milliseconds is usually a better measurement. But we want to process frames as fast as possible. We have a secondary goal, which can be kind of conflicting with the first goal, which is to minimize latency. So the time from when a user makes some input until that the result of that input is visible, is rendered out. Especially important for VR, of course, where you will get really sick if the latency gets too high. Typically, so these are the main goals. So sort of a corollary to that is that we want to keep the cores as busy as possible. So if we're looking at sort of a performance diagram and we see that some cores aren't doing anything, that's a bad thing. We definitely want to make sure that we put all the cores to work. But we want to do that doing actual work. So cores being busy does not necessarily mean that actual work is done, because there could be a lot of overhead if where codes are busy, they're doing something, but they're not actually doing the work that we want them to do. They're just communicating or locking or syncing in some other way as that. But usually we take busy cores as a sign that things are good, unless we have something stupid in our system. So the thread model in the engine, we have sort of three different kinds of threads. So we have two main threads, sort of. One is the main thread. Maybe that's confusing. Should call that the update thread maybe, and one render thread. And these are sort of main processing threads. And these threads run pipelined. So we will update one frame at the same time on one core, at the same time that we're rendering the previous frame on another core. And then we'll have a passover point when that frame is done. The data from the update thread will be sent over to the render thread, and the renderer will render that frame, while the update will start updating the next frame. And by update, I mean things like running scripts, running animations, running physics and stuff like that, while render is basically gathering all the commands for submission to the GPU and doing stuff like culling and stuff like that. So these are the two main threads that sort of drive the whole process. And then we have a number of worker threads, and these threads are used to process jobs. So whenever the update thread or the render thread has to do something that is computationally expensive, it will divide that task up into multiple jobs, so that multiple worker threads can be used to process that, to process the jobs. Finally, we also have some threads for asynchronous tasks. These threads typically sleep most of the time, and then they're awakened by the OS on like network input or file read completion or stuff like that. But these threads spend the most of their time sleeping, so we don't really worry about those threads too much in this talk. These are the ones we focus on, the main threads and the worker threads. As you can see here, kind of immediately, is that we have a latency which is twice the time it takes to update or render a frame, because we have this two-stage pipeline. So it first has to go to the update stage and then to the render stage. And then we have display lag as well. So we have we have a bit of extra latency here because we stagger the update and render thread. So you might wonder, why do we do this pipeline thing? Why don't we just update and render this one frame on the same thread? I mean, we could use the other thread here. We can use that as a worker thread and just add that to the worker pool and do jobs from this thread here. The reason that we're doing it pipeline like this is that both in the update thread and in the render thread, we have quite large single-threaded parts. Especially in the update thread, we have the script update, which is single-threaded, and during those single-threaded tasks, the worker threads won't be doing anything. So if we just had this on a single thread, the worker threads would be completely idle during those single-threaded parts, and we would lose a lot of the performance. But by pipelining it this way, that means that if the update thread is in a single-threaded section, hopefully the render thread has some job to do to farm out to the worker threads. And similarly, if the render thread is running single-threaded for some section, the update thread maybe can run some job on the worker threads. So in this way, we can actually use the worker threads a lot better. And you can see the difference. The engine, you can disable this in the engine and run the update and render on the same thread, and you can see that it really hurts performance. So by doing this pipeline, we can sort of fill these single-threaded holes in the update. So the main and the render thread are processing the data pipeline in different stages. They need to be synchronized somehow, and we do that synchronization by keeping a copy of the state. So the render thread actually has a copy of all the mutable state that the update thread has. And by that mutable state, I mean things like the positions of objects, the colors of things and stuff like that, colors of lights. But one important thing to notice is that the render thread doesn't have a complete representation. It doesn't exactly match what we have on the update thread. Instead, the render thread only has the things that it actually needs to render. So, for example, in the update thread, we care about the local positions of objects because we want to evaluate the scene graph and go from the root and transform everything to find out the world position of objects. The render thread doesn't really care about the local position of objects because that's not used when rendering. They're just rendered at their world position. So we actually just mirror the world position to the render thread. And the same applies to a lot of other things. Basically, we want to mirror as little as possible because it costs time to send that data between the threads, and also it uses more memory. But mainly it's because it costs time to send the update. So we make sure that the render thread only has the stuff it actually needs to render things. So the way this kind of works is that when something happens on the main thread or the update thread, like an object is created or modified or destroyed, we post commands to mirror this action. And these are posted to sort of a queue that is consumed by the render thread. So we post commands like create an object with this ID of this type, and here's some data for the object. Modify this object, change its word position maybe, here is some data for that. Destroy this object, and so on. So the renderer, so all this will be posted at sort of the end of the update here. When the update has completed, all this is posted to the render thread, and when the render thread gets here, it can start consuming those modifications and mirror the state of the main thread. Note that since these states are completely separate, so there's no need for locking. Since we do a complete copy of the state, there's no need for locking, and we don't have to care about like when in the frame we delete the state for the update thread. We can throw that away at any point because the render thread has its own copy, so it doesn't matter if the render thread is busy rendering those exact objects at that time. We don't copy the immutable state, and the immutable state are things like vertex buffers, geometry, textures, stuff like that. We don't copy that because that would be expensive and it's kind of unnecessary since it doesn't change. So instead, for this immutable state, we have to take some care to synchronize the creation and deletion of this state so that the main thread can't just delete the immutable objects, because then they would be the render thread could be using those objects at that time. So in this case, for these objects, typically the ownership is on the render thread, and the main thread sends a command to release them to the render thread. The render thread takes care of it, so it can be synchronized with the rendering of these objects. So for the worker threads, we try to spawn as many of the worker threads we need to get one thread per core. We want one thread per core because we don't want to, if we have fewer than one thread per core, then we're not utilizing all the cores of the system, which of course would be really bad. If we have more than one thread per core, we will probably get context switched out by the OS a lot, which is really bad. Context switching takes a lot of time, and I mean, only one core can be working at one thread at one time anyway. So we try to match. So for example, if you have an 8-core machine, we will spawn 6 worker threads, because we have the main thread or the update thread, we have the render thread, and then we have room for 6 more threads, and then we filled up the other core. We don't really care about these asynchronous tasks that I talked about, these asynchronous processing threads, because they are typically not consuming a full core. They're just doing a little bit of work and going back to sleep, and doing a little bit of work and going back to sleep. So we don't really count them when we do this core allocation. So these worker threads are used to process jobs. The way it works is that the main thread and the render thread post jobs to a queue, and the worker threads pull jobs from this queue to perform them. The main and render thread can wait for a particular job to finish. So they post some jobs and then they wait for them to finish. Important thing to note is that while they are waiting for a job to finish, they will act as worker threads. So if the main thread posts a bunch of jobs and then waits for them to finish, while it's waiting, it will do jobs. And this is really important, because without that, we would not utilize all the cores, because the main thread would just be stalled. So to utilize all the cores, and since we have one thread per core, it's really important that they also process jobs while they are waiting. In most cases in the engine code, we branch and join quickly when we post jobs, and by that I mean that we have a main thread that is doing something single threaded. Then it comes to a portion where it needs to do some data crunching, say an animation update. Then it will spawn a bunch of jobs, and sort of the processing will go wide on a number of cores, processing just those jobs, and then they will all finish. We'll wait for them to finish, and then we'll continue the logic single-threadedly. So you can see this, for example, in the animation player, which is one system that uses this. So we'll go into this a bit more later maybe, but it goes through all the animation that it wants to update. It sets up the data for the jobs, for the different animations that it needs to evaluate. Then it posts a job, and then sort of immediately after the job has been posted, it waits for the job to finish, and then it continues to run sort of single-threaded after that. So this is not perhaps the most efficient way of doing things, because we only go wide and utilize a bunch of cores for that short period of time, and then we're back to being single-threaded. As I said before, it doesn't matter as much because we have the 2 pipeline threads the main thread and the render thread. So while we're single-threaded, we can hopefully do some work for the render thread on the course. But you could argue that it would be better, instead of like posting the jobs and waiting for them immediately, we could post the jobs, go do some other stuff unrelated to animation. Maybe go do some physics, post jobs for that, and only wait for these animation jobs to finish when we actually need them. So a lot later, maybe in the processing time. So doing that, sort of joining the threads later, waiting for the results later, would allow us to utilize the course a bit better. We would probably be able to fill the course better. We would have less of these single-threaded portions in the code. But this is also a lot harder to reason about, because suddenly you now have, if you do this, you suddenly have animation data. The animation data is being processed, so it's not in a stable state. So if some other system needs some data from the animation, then we start to have problems. Should it use the data from the previous frame, or should it use like some mix of the current frame or the previous frame? Do we need to double buffer the data? Do we need to copy the data? How exactly does the data flow between these different systems? Which systems are dependent on other systems? It becomes a lot harder to reason about, while as when we're doing it sort of this single-threaded branch out, it is easier to reason about, because we can have a logic flow that is easier to follow. Like, well, first we update all the animations, then we update all the physics, and then we mirror the results to the render thread, and so on. It's kind of easier to follow the way the logic flows. So this is sort of a thing you could think about a bit more. And it's also, being a general purpose engine makes this a bit harder. If we were just an engine for a particular game, you could write out exactly the data flows you wanted for this game, adapted to how much time each system typically used for this game. But since we're a general purpose engine, we don't really know exactly. Someone might use our engine and do a ton of physics but no animation. Someone else may have a lot of animation, no physics. Someone may have a lot of script but no physics and animation. So sort of planning exactly how the data should flow between all the systems becomes pretty complicated if you want to go away from the sort of single-threaded model we have today. But it's something we should consider, I think, for the future. At least have it in the back of our heads and think about, well, do we want to redo this somehow to use the course better? But so it's a trade-off between having a system that's easy to understand and have a system that is more performant. And sometimes a system that is easier to understand can, in the long run, become more performant, because you can better reason about its performance and it's easier to do optimizations. Whereas if you build something really complicated, maybe it's so hard to reason about that nobody can really figure out where the time is being spent, and nobody can do optimizations. And then, even though in theory you have a more efficient system, it may end up not being as efficient in practice. So it's a tricky balance between these two things. We have a class called the Thread Manager, which is responsible for creating and destroying threads. So this class is basically just a wrapper around the thread support that the OS has. So this is used if you want to create some special thread, like one of these background threads for some specific task. It's also used to map thread IDs to thread names. If we have an error somewhere, we can print a useful name for that thread. The Job Manager class is a class that manages this sort of pool of worker threads, and you post jobs to this. You post jobs to the Job Manager, and it looks something like this. We have an abstract interface to represent a job, and for this job you can set input channels with IDs. So if it's a job performing transforms, for instance, one input channel could be the local transforms, another of the objects, another input channel could be the parent transforms of the parent objects, and so on. And you can set constants for this job. It has a kernel, which is, the kernel is a function that will be called back to actually perform the job. So that function will be called back on all the different worker threads. And together with sort of this job, you specify a slice setting, which specifies how the job should be sliced up into tasks for all the different cores. So typically a job has a size like 1,000, and then it might have a slice setting that says, well, we should take each 100 things and do them as one task. So then you will get 10 different tasks, and they will be queued on the different threads. So in the kernel code, you can query for these streams that were set up and get back the data for the particular chunk that your kernel is working on. So the job system will actually split the job up into chunk based on the slice setting we've set, and then do a callback on the worker thread for each of these chunks. So we can have a look how this looks, what this looks like in the code. We have some update here, I guess. Just here, let's see. Here is the kernel for the update. It gets, this is for the animation blenders. I'll talk about them later, but it just runs a certain update functions on a bunch of these. So it gets chunk, size of that chunk, how many objects we have to update, and then it runs the update function for these objects. So it's not super complicated. And this is the function that queues the jobs. It sets up the input to feed in the Blender objects and some other data. It sets the count, the number of things we have to do. It sets a constant, which is the time that has passed, which will be used by this job. Then it runs the jobs with default slice setting and wait for the jobs to finish. This is again one of these split and then join immediately. So it's not super complicated, but I would still say that this system suffers a bit from over design. I think this defining all these channels and setting up input and output channels and getting them back later, it just seems overly complicated to me. It might be better to say that the job is just like a blob, like a struct, a raw struct that is passed down to the kernel, together with like an index of which subtask of this job, like how many chunks has this been split up into and which chunk are we processing. And then this blob could contain all the pointers we need, all the constant data or whatever. It would just be a struct with that data. And the kernel code could cast it to the correct struct and then do the whatever calculation it needs to find out the portion of the pointer arrays that this kernel needs to work on. I think that would simplify this system quite a lot and create. I don't see the need for creating all these streams and having these slice objects. I think it's over designed. So I think this is a target for refactoring. Yeah, you can look into Job Manager CPP and Thread Pool CPP, which manages the worker threads. You can see sort of the job algorithm code. I won't go into that here, but how these different worker threads synchronize to pull jobs from the queue without doing too much locking and becoming locked up that way. We have critical sections, which we use to prevent race conditions and make functions thread safe. This is a class that translates into a lightweight mutex on all systems. And by a lightweight mutex, I mean that a mutex that typically first tries to spin lock for a short while, like it's up to the OS usually, but spin locks for a short while trying to obtain the lock, and only if it can't succeed in spin locking, then it will actually go down and do an OS call and get the real mutex and stuff like that. So usually these are quite effective, since usually they don't have to do a full OS call. They can just, especially if there is low contention. If the contention starts to get high, then this starts to get really expensive. This is what I talked about a bit in the memory system, where we have a lot of these locks, and we also have a lot of memory allocation. So there you actually get a significant amount of contention, and you can see how it affects performance. But in most systems where we just use this for sort of thread safety, there's usually not a lot of contention, and it's not a big problem. So there's two classes here. There's first a critical section that represents this sort of mutex object, or lightweight mutex object. And then there's a critical section holder, which is sort of which is an object that will hold the critical section for as long as it exists. So typically you use that as a scoped object. You put it at the start of a function, and the constructor will obtain the critical section, and when the object is destroyed, when the function exits, we release the critical section. So that way you don't have to keep track of, if you return early, for instance, you don't have to keep track that you're releasing the critical section yourself. It's handled automatically by the destructor. Sometimes these critical sections can sometimes be a bit vague in the code, I would say. Sometimes you see a critical section in a class and it's just named _CS or something not very well defined. And it can be kind of hard to tell, well, what is this critical section actually protecting? Is it protecting all of this class, or just some of the variables in it? What is it actually used for? And especially if you start to have like multiple critical sections in a class, that can really mess up your head trying to figure out what actually locks what. So there is a pattern we use in some places where I sort of refactor this to make it a bit easier to figure out what's going on. For example, in the resource manager, we have an example of this. So to make it sort of, because this class, the resource manager, has a lot of different members, and a lot of these are sort of static, like the version, for instance, type globals. So the sort of static objects don't really need critical section synchronization, because they're only touched when they're only like mutated at in a setup stage, and after that they're immutable. So they don't really need critical section protection. But then there are other variables that need critical section protection. So to sort of keep it clear in our head, we have a struct that contains all the variables that should be under this critical section, called locked vars in this case. So these are those variables that need to be protected, and then we have a member that stores all these variables, but we never access this variable directly. Instead, we do it through a lock. So we obtain a lock on the class. This is the name of this class. Create this variable, and the lock will then obtain the critical section, and it will also expose the variables through this member. So as long as we have the lock, we can access the members, and it's fine. And we can also, if we need to do a call to a sub-function, because that's usually what can mess you up with critical sections. You call another function and you don't know, well, in that function, will I always be called from a function that has the lock, or might I be called from a function that has not, that doesn't have the critical section? Do I have to take a critical section myself in this function? and that can become really confusing. But with this lock structure, you can pass the lock around. So if you have a function that assumes that the critical section is held, then that function will take the lock as a parameter, and it can use and it will know that the person who is passing the lock is holding the critical section, and it can use the sort of vars member of the lock to access the locked variables. So I kind of like this construct. It keeps things clearer about what is locked by the critical section, what is not. But there's still a lot of places where we haven't sort of rewritten it to use this construct where we just use the critical section straight away. There's also a class for wrapping events, like OS events. I won't go into that, but you can look into it if you're interested. So, wanted to continue with some more like general discussion about threads in the onion, because it's a complicated topic. So to begin with, thread safety. The onion is not generally thread safe. There's not. You shouldn't assume that systems in the onion are thread safe, because by default they're not. And the reason for that is, of course, that making everything thread safe tends to be kind of expensive. You either have to introduce a lot of locks, or you have to do double buffering or something fancy like that. So the only thread safe systems in the onion are the systems that need it. And by that, I mean, for example, memory allocators. We will want to do memory allocation for multiple threads, except the temp allocator that as I said when I talked about the memory system, that you can't pass the temp allocator between threads. But other than that, the memory allocators are thread safe. The resource manager is thread safe, because typically multiple threads will need to be able to access resources, and so on. But everything related to this is poorly documented and not super well thought through. There is no place you can go and read to find out exactly which systems in the onion are thread safe and which are not. Even functions are usually not documented as to whether they are thread safe or whether they are not thread safe. And there hasn't been a systematic approach where we sort of sat down and thought about, okay, what systems should be thread safe, what systems shouldn't be thread safe. Instead, we've sort of added thread safety to the systems as they've needed it, as we've gone along. I think we do a pretty bad job here, especially with documentation. And in fact, I think this is something that a lot of APIs are pretty bad at, exactly documenting, because the thread thing, like if something is threaded safe or not, exactly how it's thread safe, like can I call this function at the same time as this function, or can I call just this function, then it's thread safe. That's kind of an external factor, so people don't really think about, and we don't either, but people don't really think about documenting that stuff as important as, I mean, people document what the function does. This function does this. And then there are some implicit requirements in their head, which is like, well, you can't call this function at the same time as this function if you do it from another thread, and so on, which is never documented. So I think in general, as multi-threaded programming becomes more and more important, as we get more and more cores, we really need to get better at documenting this kind of stuff. And also, I think that this whole thing, like thread safety in the onion, maybe needs to rethink. Maybe you should sit down and think about, well, what do we really think about thread safety? Are there more systems that we should make thread safe? How do we want to work this? And I'll talk more about that a bit later. So another thing you might ask is, why do we have two main threads? Why isn't everything just a loose collection of jobs and data flows from one job to another, from an animation job to a physics job into a rendering job, and so on? Why do we even need these sort of main threads? Can't it just be a collection of cooperating jobs? And I'm pretty sure it could be. It would require a bit of a rethink. I think the advantage of having these main threads sort of is that it makes it easier to reason about the system. We can reason about how the data flows. It's kind of easy to see. It's easier to reason about the lifetimes of things. It's easier to reason about memory use because we know how long, if we have like some temporary memory that we use, we know how long we will need that memory. And the fewer threads you have, the easier these things are to reason about. Like if you have just one thread, it's super easy. If you have two threads, which we have two main threads, the main and the renderer thread, it's easier. All we have to think about is this mirroring between the main thread and the render thread, the queuing of that state and duplication of that state. If we start even more loosely coupling, it makes it harder to reason about. So similar to what I said before, it might make sense, I think, to go for something more loosely coupled. I think it could be good performance-wise and sort of interesting design challenge. But it's hard to reason about, and we need to if we go for that, we need to make sure that the increased complexity doesn't eat up all the performance gains we potentially get from a looser structure. Fibers is another thing I think we should look into. There was a good talk from Naughty Dog on that, on using, I think it was Naughty Dog at least, on using fibers in the onion, and I think that's something interesting that we definitely should consider for the future. Another threading issue that we run into is how to prioritize jobs. As you saw there, we have both the main thread and the render thread can be queuing jobs. So at any point in time, we can have multiple jobs from the main thread and the render thread. So the question is, what jobs should the job manager focus on? Should it be render jobs or main thread jobs? And if we're looking for maximum performance, that's what we should do sort of depends on what the critical path is. If we happen to be render thread bound, like the render thread is where we're spending most of the time, then it's more important to focus on the render thread jobs so that thread doesn't get delayed even more. If we're bound by the update thread, then it's more important to do update threads. We don't really know this, again, because we're a general engine. We don't know how it will be used. So we can't upfront know which thread will be the most busy one. You could optimize this for a specific game. If you find out that, well, it's always the update thread that's more busy, then you could say, well, we should always prioritize update thread jobs. But in general, it's hard to do. You could do it dynamically, like you could try to measure, does it seem like we're main thread bound? Okay, then give higher priority to the main thread jobs. Does it seem like we're render thread bound? I'll give more priority to those jobs. But again, this adds complexity, and anything dynamic is kind of tricky because it makes it can create these kinds of feedback loops where it's harder. It makes it harder to just take a frame snapshot and figure out what is going on, because maybe you have to run it for 20 frames for sort of this optimization algorithm to figure out how the jobs should be balanced. And maybe you can get into sort of a ping pong state where all the jobs are put on the update thread, and then that one runs too slow, so all the jobs are moved to the render thread, and so on. So I generally try to avoid these kind of dynamic optimizations where the system changes how it behaves based on some measure of its performance, because it creates these strange feedback loops. I think it is something useful, and it's something you could do to, again, maybe to optimize a specific game or something, but it's also something a bit scary and a bit hard to control. So I tend to avoid those kind of optimizations unless they're very, very specific, like dropping the renderer resolution if the GPU load gets too heavy, which a lot of games are doing these days. That's kind of a very isolated thing, so I feel better about doing that than about like reprioritizing how jobs are scheduled and so on. But something that could be looked into. Another important threading issue that we've been discussing for a long time but still don't have a good solution to is multi-threading gameplay code. So the problem here is that a big chunk of the update task is the gameplay code. So Lua script or C code if the gameplay code is written in C. And that code is single-threaded, which means that during that chunk we're not getting any other work done on the other cores, except the render thread is doing something with them, maybe, if we're lucky. But as we get more and more cores, this becomes a bigger and bigger problem. This single-threadedness of this section becomes more and more important, and become more and more limited by the single-threaded gameplay code. Usually our users write the gameplay code in Lua, which makes this harder because Lua has no multi-thread support built in. We can multi-thread Luas kind of by running multiple Lua states. So there's a project called Lua Lanes that you can look into that's related to this if you're curious. But basically what you do is that you run multiple Lua states, one on each core, and then to multi-thread a piece of Lua code, you send it out, you sort of package it into some isolated piece, you send it out to one of these separate Lua states, they run the code and send back the results to your main Lua thread or whatever. So this kind of works well for simple examples, but once you get into something like real gameplay code, I find that it doesn't really work. It's really hard to, if you have a problem in gameplay code, it's really hard to break it down into isolated tasks that you can send off to a separate core where there is a small amount of data to send, because if you send too much data, then all your time will be spent sending data back and forth. But where there's a small amount of data to send, and then a large sort of computational task to do, because that's what you need in order for that system to be effective. And those problems don't really occur that often. I mean the reason why they don't occur that often is that whenever we have a problem like that, we try to do it in the engine, because that's what the engine does, like hard crunching on data. We write solutions in C, we make sure we multi-thread them and so on, and we hard crunch the data. So whatever is sort of left in the gameplay layer tends to be this sprawling stuff, like things where it touches a lot of things, it does a raycast there, it hits something, oh, then it does some damage to an object and spawns a particle effect, plays a sound, like touches 1,000 different systems in like a sprawling way that's really, really hard to break down into something efficient. So that's really tricky to how to organize the gameplay code even into something efficient. Another thing here, I mean, it's easy to get stuck in this. It's easy to get stuck in the technical task, like how do we multi-thread Lua and sort of try to solve that. But we also need to solve sort of the social task or whatever. We need to solve. We don't just need to solve the problem for the engine. We need to solve the actual issue that the gameplay programmers have, and that means that we need a multi-threading model that is easy enough to understand by gameplay programmers. Now, if you have a multi-threading model that is based on the gameplay programmers understanding some lock-free code and coding that by hand, then no gameplay programmers will be able to use it efficiently. It will just be too complicated and error-prone. So that's important as well when thinking about this. We have to think about, well, how can we make it easy to write multi-threaded gameplay code? And I think the only model I've seen that is easy is sort of the actor model, where you have sort of independent actors that receive and send messages to each other. So I think something like that is probably what you want to do for multi-threaded gameplay code. I think that's the only multi-threading model I've seen that is really easy to use. But even if we did this, if we implemented the actor model, we have another big problem, and that is, as I said before, our systems are not thread safe. And if you look at what gameplay code does, it will call into systems. That's what it does. It will call into the renderer or animate something, play sound, play particle effect, and so on. So unless all those calls to all these different systems are thread safe, then we can't really multiplay the gameplay code anyway, at least not in any efficient way. So,
however, the problem is that even if you render it thread safe, you often end up in a situation where there's so much contention that it's not.
Yeah, exactly. So you really need to think about, totally. So you really need to think about, I mean, just adding locks everywhere doesn't solve it. Then you get so much contention that you don't gain anything from the multi-threadedness. So I think sort of thinking about multi-threading gameplay code, the first step is really to think about the thread safety model. And I think it can't be locks everywhere because that's too slow. It has to be maybe state copying, like having multiple representations of the state, one that is being mutated, maybe mutating commands end up on a queue rather than being performed directly and stuff like that. But so this is a huge task because it affects all the systems in the onion. If you want to be able to multi-thread gameplay code, and gameplay code touches everything, then you have to do this for sort of all the systems in the onion. So before we've solved this, it doesn't really gain us a lot to think about multi-threading Lua or multi-threading gameplay code. We really need to solve this thread safety thing first and solve it in a performant way, because otherwise there's no point to this at all. So I crammed in also a little bit about our how timing works here, since it's a bit related to threads, and but it's kind of separate from threading stuff. But I wanted to have it somewhere. Timing in the onion works. We sample the real world time. We have a class for that, or a function for that in timer. This is a bit of a strange interface because we don't want to expose what the time means, so we only have a delta function, which means that you can't get a time value that says what the time is right now. Instead, you can only get differences. So if you want to measure some time, you have to take a delta first, and the delta function here will update this one to represent the value passed in to represent the current time. And then you take a delta at some later point, and then it will return the seconds elapsed between these 2 points in time. So that's sort of the way we get time in. Then we translate that into in-game time through a class that's called time step policy, which has a lot of special stuff in it for handling how we should time step. It has multipliers. You can slow down time or speed up time for slow motion effects and stuff like that. It's supposed both fixed or variable time stepping, although by default in the onion we always use variable time stepping rather than fixed time stepping. But you may want to use, because the reason is we want to run as fast as possible usually. It has support for throttling, like setting a max frame rate, which you might want to do on a laptop, for instance, to save battery, rather than running the game at 300 FPS, which the user might not care about, and burning through all the battery in 1 hour. It might be better to clamp it at 60 FPS and have a longer playing time. There is smoothing there, so we smooth the time step that we sample over a couple of frames. And the reason we smooth the time step is because some gameplay algorithms behave better with a fixed time step. A typical example of that is if you have some code for following a user. If you have one object following another object, and you want to take a step closer to that other object based on how long your time step was. If you have really oscillating time steps, then the steps that you will take will oscillate too, and it will create sort of a vibration when you're looking at that object. It's not self-evident that it happens, but if you look down and see look at it, you can see that those kinds of situations, for example, when one object follows another, you have like secondary effects. If you only have first order effects, it doesn't matter. It doesn't matter if the time step is long or short. Like if you only have speed, for instance, because you will move with the speed multiplied by the time step, so you're not affected by the time step. But there are situations where you have second order effects where the time step actually starts to matter. So doing some smoothing improves those algorithms and makes it closer to what you would get with using fixed time step. It also has minimum and maximum time step, and that's usually for preventing bugs, because some algorithms don't behave good if you have a 0 time step, for instance. They may freak out. Also, they may not behave so good if you have a long time step, which becomes really important when you're debugging a game and you're broken in the debugger trying to figure out for 5 minutes. If you then let go and the system would take a 5-minute time step, then your character would run off like a kilometer off the map or whatever. So it's useful to have a maximum time step. There's also a depth payback mechanism to keep us in sync with the world clock if we need to do that. Usually that's for multiplayer, because some of these, like the smoothing or having a maximum time step and so on, that can cause us to drift from the world clock. If 5 minutes passed in the world, but we only take a 1 second time step, then suddenly our clock is off from the world clock by 4 minutes and 59 seconds. And if it's important to keep in sync with the world clock, then we need to get that back somehow. So we will then add sort of extra fake time to the next steps in order to get back in sync. Yeah, as I said, we use variable time stepping for world update, but we step some systems like physics. We actually step at a fixed rate, and because physics doesn't behave well with variable time steps. So we step it at a fixed rate, but just take as many steps as we need to keep up with the variable time step we have in the engine. So that was everything for this. Are there any questions? All right, let's take a 3-minute break and continue with talking about testing.